card. Okay. So the last day, we talked about the Pythagorean identities, and we used them to solve some equations that lend themselves to being solved by those. And then we even looked at some identities, some other identities that we can use the Pythagorean identities to prove. And I think we came as far as the compound angle identities, like cos of A plus B, sine of A plus B, tan of A plus B. I think we got those three. We use them to solve equations as well as to prove some other identity. So what we're going to focus on this afternoon is, well, not just this, but this is one of the topics we'll talk about. That's the double angle identity, right? Double angle identity. And these are the double angle identities here, right? Basically, they're telling you if you take the compound angle identity, and where you see B, you put another A there. So what will happen is that you're going to have 2A, right? So sine of 2A, cos of 2A, tan of 2A, right? That's what you're going to get. And if you put those inside of where you see B, right? You put A, you're going to get these identities. Sine 2A being this, cos 2A being that, tan 2A being that, right? So these are three new identities. When you watch them alone, you can see ways of memorizing them, right? When we were young boys and we were studying this kind of thing, we found ways of memorizing because those times our teachers were tough. They want you to use your brain. And memory is very important, strong memories. I think nowadays we say, man, everything there on the internet, so don't worry about strengthening memory, right? I am not sure that's a good trend because not that there are studies to prove this, but I think there will be, right? People would have to get into the question of, with all this information available on the internet, and students aren't pressed to memorize things, Now, with not using that part of your brain that deals with memory so much, right? Well, could it lead to, the kind of things you see people having a lot of dementia now, and they're having trouble. I don't know. Some of you here might very well say, "So I already start forgetting things easily," right? But strengthening memory is a good thing. It's not a bad thing. You don't have to worry that your brain is going to fill up, right? Strengthening is good, right? Not everything you got to put it in your calendar, in your you have to write it down in a notebook, right? Um, you wanna use your memory, try to strengthen it by memorizing things, right? And of course, you don't want to memorize everything, right? Usually, people tend to memorize and remember things that you're interested in, that is important to them. Well, I would think, the formulas you're learning in these courses are important to you. They are of value to you, of importance, and therefore, putting some effort there is not a bad thing. Nevertheless, I mean, your test and so is all going to be open book. You can actually go and, or you can have a formula sheet and write it down. That's no problem, right? But I'm just making a general comment that strengthening memory and, doing memory exercises is not a bad thing, right? People don't see the use of it, right? It's when you get older then you realize, what? It's just strengthening memory. Yeah, use these things just to show that. Yeah, so these three here. And what are we going to do with them? We're going to solve some equations, that they can help us to solve, and we're going to even prove some identity, right? Before we move away though, this second one is interesting because we can actually, have the different versions of it. As you can see here, where you see sine square A, you are replacing it with, where you see cos square A, you can replace it with 1 minus sine square A. And you remember where we get that from, right? Remember that thing? What is it? One of the Pythagorean identities. I think I my tablet, my writing tablet here. Yeah, yeah, no. My writing tablet is supposed to cover the entire screen. Okay, all right. So you remember the identity sine square theta plus cos square theta equal 1. Remember that thing, right? So from this, you get that cos square A is the same as 1 minus sine square A, right? You put that in here and the whole expression becomes this. This is an alternative form for that, right? And similarly, you can replace sine square A with something and becomes this, right? These are all useful identities, right? They're summarized here for us. So the second one here, well, we have 3 versions of it, alternative versions of it that might very well be useful, right? And that's where the more you have to solve problems involving these, you know that, well, okay, the merrier, right? More identities, portable identities, you call them. Those are established. Everybody knows them. And therefore, you can use them to solve less known, prove less known identities or a certain trigonometric equation. My tablet is saying, let me do this here. Cut it off and put it on that one. No, now I'm making use of the whole tab. Okay, good. So now we have them, right? And then we can take them and do something for them. You notice here? We can take these here. That's this one and this one. Rearrange it and get that. Take this one and this one here. Rearrange it and get that, right? So these are all, once you know the identities from the beginning, you could always transform them for whatever uses you might find yourself needing them for, right? Good. So let's use them. Let's use them to see if we can solve some equations and prove other identities and so on. Look at this one. So you want to solve this equation, cos 2x plus 3 sin x equal 2. Right? What do we do? Well, we can take this piece here and we using, well, you see there's a sign here. See, you're looking above here and you're looking for, okay, is there one of these that has sign inside, right? Right? So you got cos here. We don't want another cos to complicate it. Right? We want to have maybe everything with sign. So this one seems to be a good one. We take that, take it, all right. And we apply it here. So where we see cos 2x, we are going to put 1 minus 2 sine square a, right? Put it there. So you remove some bracket, you simplify, you bring everything to one side so you don't have any negatives sticking out here, right? And for those who, when they look at this, they might say, man, well, I can't see how I could factorize this to get this, So remember I suggested the last time, if you want to you can let sine x be equal to, maybe a big X. So this becomes 2x squared. This becomes minus 3x, and that becomes 1 equals 0. And you have something that you're familiar with. You can factorize it, and you should have 2x minus 1, x minus 1 equals 0. And then you can put back. You can even solve for x. You can put x equal to a half or x equal 1, and then put back. Where you see x, you put sine x, right? You will do that if, you're having trouble working with sine x of itself in the equation, right? So you suit yourself if you're, you can't work with the sine x, and so in the equation, you want to convert it to this and proceed. It's up to you. Up to you. So we solved there, we got sine x. We need to find the angles of themselves, right? And they want a general solution. Go into that. So now that we have sine x equal a half or 1, let's get the general solution. So you're taking when sine x equal half, right? So the principal solution will be pi upon 6, right? And the secondary solution is going to be pi minus pi upon 6. And that's what you got this here, right? Pi minus pi upon 6, right? Let me just clarify that. If you watch this here, let me go. This is going to be 2n pi plus, right? Plus pi minus pi upon 6, right? So this is the piece, right? This is the secondary value. Secondary value. So all the people did is they paired this piece, factorize it. So it looked kind of weird. You say, oh, well, we're going to put this from somewhere. So this is the secondary value here, right? But they did their, well, remember textbook writing, they want to polish it up and make it look nice. So those are the two general solutions there. And then you go with sine x equal to 1. The principal solution is pi over 2. And that's your general solution, right? So every time a graph peaks here is a solution, right? And you realize that that happens every 2 pi, right? N can be negative or positive, right? N doesn't mean natural number here. N can be any integer, right? Yes, they should have said, N is an element of Z, right? See. Any questions? Feel free to slow me down, So there we have, okay, an equation. And well, okay, they write both general solutions here, right? 3 of them is that. This one, and this one. Right? And they have all kinds of other problems that they can ask you that you can make use of the double angle identities, right? So look at another. Take this off a little more. Good. So they give you tan theta equals 3/4. And theta is acute, they're telling you. Find the values of tan 2 theta, tan 4 theta, and tan theta upon 2, right? You can see that there. They give you this, they give you this bit of information, and you have to find this, and this, right? So, well, remember this one. This is the double angle identity for tan, right? So tan 2 theta, you just got to put 2 tan theta here, 2 tan theta squared here, you know. You already know tan theta is 3/4. So 2 times tan 3/4, sorry, is going to be this. 1 minus 3/4 square is going to give you that. Simplify and you get that. Right, watch it work. Now tan 4 theta can be written as this now. Tan 4 theta is in the formula, you replace theta with 2 theta, right? Because this is normally twice that. Now you just found tan 2 theta here. You just found tan 2 theta to be this. So you put that now in the place of this here, right? And this here. And you do whatever you have to do and you simplify, you get that. Right? But now the third one, let me erase some of this stuff here. So I think I'm doing this, whole is using this annotation tool wrong. I should have used the what is this program name again? Zoom. I could use the Zoom annotation. I don't have to do. I have to erase it. Okay, good. All right, look at this one. This one is a little different, though, right? So you want they want you to find tan of theta upon 2, right? So here you're not putting something here to get this. The unknown is this here. Unknown is this here. Sorry, tan theta upon 2. That's what you want, right? And of course you can get it from there too, right? So you know that tan theta is 3/4. That was given. So what we're going to do now, we're going to take this thing here and we're going to try to do some manipulation and see what happens. Let's see what we can do with this here. Right? So what we do, we replace tan theta upon 2 with a little t. And this is a nice introduction to a new concept where we can replace tan theta upon 2 with a little t. And later on, we'll learn about what we call the little t formula, right? Where we are able to express sine, cosine, and tangent in terms of little t. And we have a very powerful set of identities that can help us to solve almost, well, not almost, so a particular set of trigonometric equation, right? So doing that replacement, let's see if I can travel, somehow get, look here. So this is the original thing up here. Look here, right? See how this is here. This is here. So we are letting tan theta upon 2 being the little t. So this becomes 2t over 1 minus t squared equals 3/4. With that now, we can do some, you know, moving around with t and so, or a little algebra, transpose, whatnot. You end up with this quadratic again, right? It's quadratic again. And you solve that and you get t equal 1/3 or minus 3, right? So remember, t is what? T is theta over 2. So we have two values for theta over 2, 1/3 or minus 3. So notice this little note here now. They told you at the beginning, theta is acute. So that value of minus 3 is invalid. We're not going to use it because an acute value of theta, if you divide it by 2, will give you another acute value, right? And the tan of an acute angle cannot be minus 3, right? So we discard of that solution. And we're going to use the one where tan theta over 2 equal to 1/3, right? That's what we need. That's what they are. they ask us for. Find tan theta over 2. They ask to find the angle of itself. Good. So those are some, little bits of equations, and so that you can solve using the double angle identity. Let's switch over. Let's switch over now to some identities now, right? Look at this one. And I noticed the book, they only did one. Right? So I have to prove that sine of 3a is identical to 3 sine a minus 4 sine a cubed, right? Or sine cube a. You usually say that. Or you think that you're cubing the a and then signing it. You're signing the a and then cubing it, right? So sine cube a. Good. So in this one, what the writer is doing is they're taking this one, this side, that's the left-hand side, and they're trying to see if they can work to give you the right-hand side, right? So they're working on the left-hand side. So sine 3a is this, sine of 2a plus a. That's a technique, That's a technique the author is using there. When you take this and you expand it using the the compound angle identity, you get this. So you see compound angle identity comes in here. Then further, you take this piece, expand it, and you get that. You take this piece, expand it to get that. Right? And mind you, remember there were several versions of cos 2a you could have used. You would want to ask me, well, sir, why them use 1 minus 2 sine squared theta and not any other? Remember, this is textbook writing. They may have done that and found that the use of those other ones might take longer to solve the problem. So they chose this one, right? You got to understand when you're writing textbook, if people write around the solution and say, you know what, this one is the most efficient, right? They wouldn't give you one that would fill the whole page. So in this case, they use this one, and you will notice kind of reasoning why. This sine square and this will give you that cube that is seen here, right? You see? So simplifying all of this, you get this. Again, they're taking this part here and putting this in place. And then you remove all the brackets now, and you will get that. And you see. Right? This one wasn't so difficult. The only thing is that I want to ask you, or how would I have guessed that this is the form I need to use? Right? Same thing here. Right? And one of the things that should give you a clue, you notice that the thing on top here got shared sign inside. So what you're trying to do is get rid of all the costs, right? Get rid of all the costs, get rid of the cost, get rid of the cost. So you see cost here, right? You want to get rid of it, so you end up with share sign. So that should give you a clue. If you have something with a set of costs inside, but I need to get rid of the costs somehow, right? Then there are some other uses, like you see here, you want to eliminate theta from the parametric equation, you call it. How do you remove the theta from it? Well, maybe you want to write it in terms of uh, x and y only. Right? So notice what I did here. So instead of writing cos 2 theta, you can write it like this. Right? So x is this, y is this, right? And what did they do next? They transpose, notice. You transpose to make cos the subject. If you take this, let's see if we can do that. You will get x plus 1 over 2. The square root of that is equals to cos theta, right? See if you agree. And from this one, what you get? You get cos theta is equal to 1 over y. Oh, so you didn't make use of this. You make use of this. So where you see cos theta, you put 1 over y. So down here, you put 1 over y squared minus 1. You didn't need it, right? And you get it. And you do some, removal of brackets and so cross multiplying. So they made use of it. They took this one, get this, put this 1 over y in the place here, 1 over y squared, and you just eliminate theta here totally, right? Cos theta totally. Okay, so you can't, no way could you find a textbook that will look at all the possibilities. So yeah, you can try some of these. I should ask the question: anybody tried like any of the exercises, like using the Pythagorean identity and the compound angle identity, and maybe solve an equation or prove an identity? Anybody tried any? Anybody in the class? Hmm? Are you still in test mode and you're finishing up your courses and you'll turn your attention to this course a little later? What's going on?
Kind of, sir. Kind of.
That's what's happening. Well, I think the test should finish this week, right? Today. You have more tests to do?
Yes, sir.
We got one on the 27th.
Uh,
This
We got
course
one
will
on the
start
11th next month, sir.
on the 11th of next month as well. So
so tell
course
me.
started late.
Oh,
Course them started late.
and these courses, your test is like, did they use a modular approach or did they do the coursework and then you have to do one big final exam at the end? What mode did the course take? What
We had
form?
a few quizzes in between, and then we'd have a final exam.
And the final exam will cover everything.
Yes.
Oh, yeah, that's tougher. That's always harder. Because you have to go from day one right up, I get you. We're not going to do this course like that. We're doing this course more in a modular form. Once you finish with trigonometry, you could forget everything. Right? Once the test is finished with trigonometry, you basically can forget everything. And we move on like that. Your third test will not involve trigonometry. Right?
Okay, sir.
The first test is what's going to involve trigonometry. Right? Keep that in mind. All right. So yeah. So, but nevertheless, right? I mean, I know you might have one or two courses more, but you cannot spend 7 days a week on those two courses. You have to realize that this course has to have its due. Yeah, you have to spend some time with this course, right? You understand? Just like
Okay,
when
sir.
you're doing 4 or 5 courses, you divided up your time.
Yes, sir.
You have 2 more exams. You can't spend, here, listen to me, I'm a student just like you, right? I've been a student all my life. You cannot study no course every day wholly, right? As a matter of fact, those who know good education psychology will tell you that that's not a good thing, right? That's not a good thing. You want to have a break from time to time doing something else, right? Understand? So what it is something else is the very content here. By doing one of those, let's say those, what is it, issues and perspectives, where you're writing all that crap. It's good to break off from that and say, let me deal with these numbers. Right? So it's good to take some time and attempt these questions. Good recreation for you. Right? All right. So you try these. I trust you'll try them. I think I gave you the answer, so you don't have to worry. right? I mean, the proofs here, you have to prove something like this. But you will know that you get a proof, right? You will know. Good. So I want to switch over attention now on this. This part here is a little tough, right? We're going to apply the some of the identities we learned before, the compound angle, double angle, and so on. We're going to apply them to what we call inverse trigonometric functions. Right? And I guess y'all were introduced to those in the last course. Arc sine, arc cos, and arc tan, right? So instead of writing it like this, instead of writing it like that, you probably know, okay, sine inverse of some number, right, equal to some angle. Cos inverse of some number equal to some angle, you know, that sort of thing. And tan inverse of some number equal to some angle, you know. But instead of writing it like this, we say arc sine, arc cos, arc tan, right? I guess you were introduced to that, I would think, in your previous school. So let's do an example or two, right? There are lots of them. I just awaken your mind to some of the things out there, you know? So here you want to, they say, find x if arc sine x plus arc cos x over 2 is equals to 5 pi over 6. So how are we going to find x here now, right? And I like these here because they really bend the mind to some extent. Right? Students often ask me, sir, how would I have known that this is the approach to solving the problem? Right? They would not have guessed the approach to solve a problem like this. And that's why, long ago, the conception behind mathematics education and other types of education was based on what we call academic rationalism. Now, what's that? You ever heard that term? Academic rationalism? Anybody ever heard the term? Y'all doing a curriculum course? Anybody doing any curriculum course? Did any curriculum course whether in college or at UG?
Yes, sir. But I've never heard that word before.
Academic rationalism. You almost type in the maybe YouTube or so and watch a video on conceptions of curriculum. Right? And I think there are 5 main ones, 5 main conceptions of curriculum. And one of them is what we call academic rationalism. And what they used to do, it was very, well, basically what some math teachers are still doing, right? Without even knowing, they're actually, or their conception of the curriculum is this. They're teaching you what past mathematicians were doing all the time. Is that what basically the math education is all about? We're teaching you the works of Pythagoras and Euclid and Newton and Leibniz, and that's what we do. We teach you what they have been doing or they have done, right? And we expect you now to learn from their way of reasoning, right? That is changing in that people are arguing that no, mathematics education should actually have another conception, and that conception has to do with what I keep repeating to you, the development of cognitive processes, right? In that mathematics should not basically, you studying the works of all these old men, right? But it should be used to develop your cognitive processes. Anyway, watch a video on conceptions of curriculum. It's interesting, right? And you almost do that. You don't worry what is taught in the classroom alone. You almost research on the subject, any particular area. If you want to get into curriculum and instruction and so on, you might want to be doing some extra reading in those areas, depending on what you want to do, right? If you want to be a measurement and evaluation specialist, you read what they're doing out there, right? Yeah. So while I've been telling you that my conception behind this course, teaching this course to you, is really to develop your cognitive processes. I'm not dismissing the idea that there is value in watching or looking at the reasoning of these past mathematicians. Because there are lots of things you can borrow from them, you can learn from them, the way they think. These men were extraordinary men, the way they think, right? You all heard that story. You all know about rational numbers, right? And there was this story where I don't know if you know that story. There was a group of people called Pythagoreans, and in those days, I'm just deviating a little, right? In those days, there was no like how some nowadays we study math as a subject. In those days, they didn't have a division between religion and science and mathematics and all of that. No, you find a lot of the priests, a lot of the monks, right? John Venn, the man who come up with the Venn diagram, he was a monk, right? You know that? So people used to they had this set of people who they call themselves Pythagoreans, and they would have certain rules and so that they live by, and they take some time to study the works of Pythagoras and other mathematicians. And so anyway, so whenever they came up with a theorem in mathematics, or not just mathematics, but in the ancient world, when they came up with a theorem, now a theorem is like a universal truth. You can't change it. It's a truth no matter what. So this guy said, all right, there was this guy who said, you know what? If you were to have a rectangle triangle, and this side is 1 and this side is 1, then this side has to be square root of 2. But guess what? You can't find the exact value of this number. You can't tell me whether it is 1 point whatever, right? So numbers of this nature was not known until then. But remember, it is based on the Pythagoras theorem. So you can't tell him how time is shooting it. It does not violate the Pythagoras theorem. So the problem with this is that the number line seem already full. All of you know about it, what I call the completeness of the number line. In that between any two numbers, there's an infinite set of numbers between here. You all have heard of that? Between 1 and 2,
Yes, sir.
there's an infinite
Okay.
there's an infinite set of numbers between those two numbers, right? So people are saying, man, if this whole number line full up here, then where are we going to put these? Where am I going to put root 2 now? You understand? Where am I going to put root 3? Where am I going to put root 5? Right? So they get this goes to the guy, and this is a legend, right? It's a story, maybe it's just for laughs, right? So they told the guy who coming up with these irrational numbers. Sorry, irrational numbers. And they say, you know what? We go in and picnic on the island out there tomorrow. So they pack up their little baskets with food and so. And they all went out there on the island. And when they came back, the guy who came up with this, he wasn't with them. What do you think they do with him? Anybody know what
They
they do?
left you.
Huh? I didn't hear that.
I said Shani Islands.
Yeah, either they left him or they killed him or drunk him or something, right? And that was very common in the ancient world. Eh? You give him too much trouble, it just put you, you get your own ideas, you have to live separate, right? Like they do with if you're a Christian, you know about John. Preaching too much, they catch you and carry you on the island of Patmos. Yeah, anyway, back to this here, but the way those people think, right, and ideas they had in solving problems might be useful. We're not saying we're throwing away. I mean, all of this that we're doing in this course is built on the works of those men, right? And while we're promoting, and anybody watch the video, by the way, I sent you about those two high school girls who came up with a new approach to solving, to proving the Pythagoras theorem. Anybody watch the video? Silence. Yeah. While we are encouraging what you all call, constructivism, and so you're encouraging students to construct their own knowledge and even new knowledge. While we're encouraging that, there's nothing wrong with going back and finding out, well, how these men used to think. How were they able to come up with this thing here, right? Because that thing provides so much useful insight. It's like you. Yes, you all said this a modern time, and your parents, you don't want to hear nothing from them, but there are times when you know for yourself, you say, you know what? Can I ask my parents, well, Daddy, Mommy, I have this challenging situation in my family, and how did you handle it when you were younger? Right? You can learn something from them. Right? Don't think you're coming to university, you know it all. Right? You can learn something from them. And similarly, you can go back to the thinking of these mathematicians, and we can get valuable insight. This is a classic case. If I give you a problem like this, I can assure you that, I know all of you are going to run to YouTube and AI. But if I give you this and say, look, solve this thing on your own, you come back next month, you still can't solve it. But borrowing from the insight of this writer now, this writer no doubt got it from somewhere else, right? I don't think she created it. But look at this. Arc sine x plus arc cos pi x over 2 is equal to 5 pi over 6. How do we approach this? So this is the approach. We say let arc sine x be theta, which implies that sine theta equal x. Right? If sine inverse x equal theta, then the sine of the angle theta is equal to x. Right? Therefore, we can put this information. We can think of x here as being x over 1, right? And sine is opposite over hypotenuse, right? You remember that? So you let the angle, you put the angle inside of a triangle here, x being the opposite side, 1 being the hypotenuse, and from Pythagoras theorem, you get this as the adjacent side, right? So you might need this later on. Leave it there. Now, next, they let arc cos x over 2 be 5, right? 5, P-H-I, 5, which implies that cos 5 is identical to x over 2. And again, you put that on a triangle. You put 5 in the triangle. The adjacent side is x. The hypotenuse is 2. And you can calculate this third side using Pythagoras theorem, right? I guess your brain start to move there. How do you get that third side, right? I don't have to tell you. I gotta tell you everything. Good. So now that we have gotten a value for arc sine x, remember that? It's theta. Arc cos x over 2 is 5. We can say that the two of them add up to 5 pi over 6, and that's what we say here. Arc sine x is theta. Arc cos x over 2 is 5. Therefore, the two of them add up to 5 pi over 6. See that reasoning? Who would have thought that? I always teach this course and students to say, sir, how would you have expected me to come up with that? And I always tell them, well, I couldn't expect it, right? I can tell you when I was a kid and doing this for the first time too, I wondered how the hell on earth would I have come up with that? But as I said, it's good to get the insight of those who went before us. Don't dismiss them totally. Yes, They're encouraging us to forge our own paths and construct our own knowledge and create new mathematics and yeah. But it doesn't mean that, you wouldn't learn anything, or borrow from ideas that went before you, right? So good. So now that we got this, all we got to do is sign both sides, right? You don't have to sign both, you can cross both sides too, right? But this author choose to find the sign of both sides. So the sine of theta plus phi equal to the sine of pi over 6. So the sine of pi over 6 is a half. So now you use your compound angle identity and expand this, and you now get what? You get this. And in this expression, you know what's sine theta, you know what's cos phi, you know what's cos theta because you can get it from here, right? Cos theta is going to be this over that. From here, sine of phi is going to be this over that, right? So you can get those things. Good. So you put all of that now. You notice here? X times x over 2 plus this times that equal to half. And well, you gotta do some hot algebra, right? Very, very complex algebra. You do some moving around and manipulation, and you end up with that complex equation. Square both sides, you end up with this very complex equation here, which simplified to, notice, they're saying that, okay, we can actually neglect x to the 4, we can just cancel both sides, right? Now, when I don't want to bring in that here. If x was tan theta, you couldn't do this, right? So basically, you cancel out the x to the 4, and you end up with this. You end up with 3x squared equals 3, which you solve, you get x equals plus or minus 1, right? Good. So remember, x is arc what? You have arc sine x and arc cos, right? Remember you got those, right? So the value of arc sine minus 1 is this. And the value of arc cos minus a half, remember x is 1, right? Sorry, minus 1 in this case. They're doing minus 1. Is that. So when you add these two up, you find that it's not equal to 5 pi over 6. So x equal minus 1 is not a solution, right? It's not a solution. However, if you use x equal 1 and you find arc sine of 1 and arc cos of a half, it will add up to 5 pi over 6, right? This 5 pi over 6 here. You could try that on your own, right? Try that on your own. Maybe you could do it now. Find, what is it? Arc sine of, what is it? 1 plus arc cos of 1 over 2. Tell me what it is. Anybody trying it? What's arc sine of 1? 90? All right, let me work with degrees. And what's our cos of a half? Anybody doing it in their calculator? Cos inverse of a half is how much? Sort here of 60 around.
That is a virtue.
How much?
Get up, get up. Hi, Shannon, she's asleep.
Oh my, somebody, You have to mute yourself, that person. I'm asking the class for our
Where you drink them?
Hello, somebody's mic needs to be muted.
Nearby.
Yeah. I was asking for
Oh, man,
our
come.
cost of a half.
Miss Nalini, your mic.
Yeah. Our cost of a half is how much? Come on, take your calculator quick, man.
60, sir.
How much?
60.
60. So 90 and 60 is how much? 150? Isn't that 5555 over 6? Is it? Check and see if that's 55 over 6. Not true? Anybody check in? Make sure you check that, right? And well, maybe another one would, let's go through another one, maybe, right? And again, the same approach. This one is a little tougher. We're gonna go through it. It shouldn't take long,
Out, make a class.
right?
But
Now, this one says you have to prove that arctan of 3 plus 2 arctan 2 equal to pi plus arcot 3. Now, what's the approach? And again, here is if you would want to know how on earth will I be able to know that this is the approach to solve the problem. And again, no doubt this author went back to, what was done before and look at some approach to solving such a problem, right? Yes. Y'all have to mute your mics, you are disturbing the class. Hello, I see like Nalini. Y'all look at some, who is it that, if your mics are muted, please mute your mic. Yeah, good. So we start with, all right. It appears that this person or this writer is taking the left-hand side and working toward the right-hand side, right? At least from the beginning. So you start off with arctan 3 equal to theta, which implies that tan theta equal 3, right? That's what we start off with here. So they take this now. Arctan 2 is 5, therefore tan phi is 2. They actually tell you that, well, they have a range of value that theta can fall into, right? Now, why? Why this is so? Again, as I said, this is funny thing with textbook writing. They chose these values deliberately so that the identity here, or this is not really an identity, it's an equation, right? Such that it will actually be proven, right? It will actually be proven. It's an equation you're proving, right? This is not an identity. Good. So the choice here is I would say purposely set. You will see it in just a moment. Good. So from this, theta plus 2 phi is this side, right? This side. So you take it, if you tan that, it will be this, right? So with this now, you know that, well, they take this now and this here, right? Because you need that, you know this? And they actually find the value of this and this, right? Which is, well, you're using another identity here, right? Which is this value. You take that, put it in there, and it all works out to give you a nice 1/3. right? It looks like a lot of work and so, but yeah, the arithmetic will work out. So now that we got this here is equal to that, right? Notice what is said here now. If theta is in this range and phi is in this range, then theta plus 2 phi will be in this range, right? Notice what they did. They added this to 2 times that and added this to 2 times that, right? And you will get that. So this falls into this range, right? Therefore, notice theta plus phi will be equal to pi plus arctan of 1/3. You think you get that? Theta plus phi, adding the 2, is equal to pi plus arctan of 1/3. The reason why I'm saying that is that the tan of theta plus 2 pi is actually equal to 1/3. Right? So arctan of 1/3 is the same as arc cot of 3. Just to clarify, just note here that while theta plus 2 phi is equals to arctan of 1/3, which is the same as arc cot 3. You want to know why we have this phi added here. The reason why is that theta plus 2 phi is not an acute angle. Arctan of 1/3 is simply, I think it's around 16 degrees or something, right? Which is not that, right? It's not in this range. So we have to add phi inside to bring it into this range because theta plus 2 phi is in the range of 3/4 pi to 3/2 pi. So we have to add the pi here, right? And that's what we have in here. Right? So arctan of 1/3 is the same as arc cot of 3. But the reason for the addition of the pi, well, it's because of the range that theta plus 2 phi falls into, right? So that clarifies it. So our equation is actually proven. I'm getting a response, yeah. And in that way, they were able to prove it's not an identity, right? It's an equation we're actually showing that it's equal, right? The right-hand side is equal to the left hand. Think about it. Think about it some more. So I won't go through there. There are a couple more that they have, and so you will try it in your own sweet time, right? Do you want a little break?
Yes, sir.
You want a 10-minute break, maybe?
That would be good, sir. Thank you.
All right. So you come back at 6:10, right? Sorry.
Yes, sir.
Okay, so this is the last, we look at this as the last set of identities. So these are referred to as the half angle identity. So when we talked a little earlier about the double angle identity, we got this as one of them, right? Now there was an exercise. Notice they talk about the previous exercise, number 11 and 12. You were asked to prove these two, right? So notice you're writing sine and cos in terms of tan A, right? Notice that sine 2A, cos 2A in terms of tan A. That's interesting. The reason why is that, remember that thought about substituting little t for tan theta over 2. So we could actually do that now, right? Where tan 2a, we call this theta, and this a becomes theta over 2, because this is half of that, right? So when we do that in all three of these identities, we end up with this, this, and this. Now, what is useful about a set of identities like these? What's useful is that you realize that we can write sine, cos, and tan in terms of a single parameter. Let me use the word parameter, or a particular unknown t. We could write, if we have an equation with sine, cos, and tan inside, we could make it all with a common. We could change that into an equation with just t inside. And we have some amount of knowledge, right? Where we can solve equations with just one unknown. So that's what we're going to do here, right? So we have tan, sine, and cos written in terms of little t, right? Let's see how we can use them. So, okay, go up here. You have an equation now. You have sine, you have cos, right? So you eliminate, the difference here. You have sine, you have cos. You have no way of solving the equation. So what we do, we replace sine theta and cos theta with the little t identity, right? Remember, sine theta is this, cos theta is this. Put all in there and then do your algebra thing, right? And you end up with this here. You finish with that now. Simplify, you get this quadratic. Factorize that quadratic, you get this. You solve for t, you get 0 or 1. Is it 0? No, it's 0. 1 minus 1 third, sorry. Minus 1 third and 1, right? Now you have to make back the substitution that tan theta over 2 is actually minus 1 third. And tan theta over 2 equal 1, right? And that takes some doing, right? So you take tan theta over 2 equal minus 1 third, and you actually, they want the angles between 0 and 360, right? So you find those angles, right? So look here. Tan theta over 2 equal minus 1 third gives you theta over 2 as 161.57 degrees. Tan theta over 2, which implies equal 1, implies that theta over 2 equals 45. Then you take over the 2 across and multiply, right? And you get those values, right? Follow that one? Shouldn't be difficult. This one has a little twist I must highlight, right? So look at this equation. There's a twist to this one that is very important. Here, you got sine theta minus cos theta equal 1, right? You do your normal t substitution, you call it. Do your algebra and you end up with this. And when you end up with this now, the temptation would be to cancel the t square on both sides. However, when you deal with sine and cos, let's say t is equal to some sine or cos, you don't have to worry. But when t is equals to something with tan, right, whether it be a tan, theta over 2 or theta, you have to understand that this is equals to this if t is equals to an infinitely large number, right? Because if t is an infinitely large number, these have no significance, right? And therefore, t squared is equal to t squared, right? Therefore, this equation is going to be equal if, of course, 2t equal 2, which means that t equal 1, or theta is either positive or negative infinity, right? Keep that in mind. Let me go that over back. That's deep. Usually, if you are solving an equation, the temptation would be to simply cancel this and cancel that, right? And you end up with 2 theta equal 2. However, especially if you all did some calculus and so, right? This expression here is going to converge, or the two numbers will actually converge if t equal to an infinitely large number, whether be positive or negative, right? The reason why is that these will not be significant. 2t minus 1 and this 1 wouldn't be significant, right? The t square is a dominant term, and it will this side will be equal to that side or approximately equal if t is positive or negative infinity, and that's why you have this here as a solution. And why this is important is that you have to understand the tan curve. If anybody remember the tan curve, tan inverse of infinity is actually equal to 90, and tan inverse of minus infinity is equals to minus 90 degrees, right? Keep that in mind. So there is a solution there that will be lost if you were to just cancel the t squared, right? So from this then, you notice, well, from this you will get this solution, but from this you will get, notice, n pi plus pi over 2. This is the 90, right? This is the 90 we're talking about. The general solution always got n pi inside for tan, right? And therefore, pi over 2 is a solution to this equation, which comes from this part here, right? And of course, you take all of this and multiply by 2, right? But they didn't do that, right? You have to take 2 and multiply everything. So pi over 2 is this. But you really want theta. Sorry, theta over 2 is equal to all of this. The theta will be, you take all this, multiply by 2. Right? They didn't finish the problem. They just left it like that. So here it is with the little t. With the little t, you can actually now solve equations that have both cos and sine, even tan inside, right? Because there is a connection between them. There's a connection between them. And that's what you see here. That's what you see in this one. That's what you see in this one, right? Keep that in mind. For this one isn't finished here, right? You have to take the 2 and multiply everything there, right? They were just highlighting something about the temptation of canceling this t square and that t square, right? Don't do that in this case. Because notice, t is tan theta plus 2. You're dealing with a tangent. And infinity will have an inverse, right? Inverse of infinity, right? Tan inverse of infinity is 90 degrees. The inverse of tan inverse of minus infinity is minus 90 degrees, right? Keep that in mind. And they really went on like that, right? We're not going to deal with this today. I'm going to stop right there. Because I think you handled enough this afternoon. We're going to pause right here. We're going to take it up from there next week. This is new stuff. It's really an alternative way of solving equations where you have cos and sine inside. All right, but with the little t, you have what you need. So we're going to deal with this next week. All right, so stop the recording.